On January 12, 2025, at precisely 3:47 UTC, something shifted faster than anyone expected. 29 million kilometers from Earth, far beyond the orbit of Mars, but still close enough for the big lenses to watch. The interstellar object known as 3I, Atlas, did something statistically absurd. Its tail, already faint, already unpredictable, flipped direction in less than 9 hours. A complete reversal. A geometric impossibility under the solar wind conditions recorded that day. The probability? Less than 1 in 20,000. But the timing is the real story. Because right now, as you're listening to this, our best instruments, the James Webb Space Telescope, the Very Large Telescope in Chile, the patch-through arrays in New Mexico, are entering a visibility gap. For the next 34 days, the sun's glare will increasingly drown the object out. A window is closing. And when it reopens in mid-February, 3 Atlas will be 12% dimmer, moving faster, and carrying a tail whose geometry no longer fits any solar model we have. The chemistry adds another layer. Early spectral readings hint at volatile ratios no comet from our system has ever shown. A sharp spike in ionized carbon that shouldn't increase during a solar wind lull. Instruments disagree. Teams argue. Observations contradict themselves. And then there's the quiet note buried inside a routine report from the Green Bank Observatory, dated January 14. Possible periodicity detected. Confidence low. Review needed. Something is happening out there. Something that isn't waiting for our telescopes to catch up. Before we go deeper, hit like, subscribe, and tell me where you're listening from. Because this story is still unfolding. In real time. With stakes higher than most people realize. This is not science fiction. This is January 2025. And this is the 3 Atlas investigation. Chapter 1. January 5th. The first hint of drift eye. The first sign that something was wrong came 7 days before the flip. It wasn't dramatic. It wasn't headline material. It was a discrepancy of 0.3 arc-seconds in photometric tracking data from the Panoramic Survey Telescope and Rapid Response System, PANSTARS, operating out of Haleakala Observatory in Hawaii. A wobble. A slight deviation in the tail's projected angle relative to the solar radiant. Most astronomers would have dismissed it as calibration noise. Dr. Yuki Tanaka didn't. Tanaka, a postdoctoral researcher at the Institute for Astronomy at the University of Hawaii, had been tracking 3I Atlas since its initial detection on December 18, 2024. She'd built her career on precision, on catching the faint signals others missed. And when she stacked the January 5th imaging frames against archived Hubble data from 2I Borisov, the second confirmed interstellar comet, which passed through our system in 2019, she noticed something unsettling. The tail wasn't behaving like Borisov's had. Borisov's tail had been textbook. A smooth, predictable fan of sublimated ice and dust pushed outward by solar radiation pressure and the solar wind. The geometry followed classical comet physics, obeying the Finson-Propstein model that had worked reliably since the 1960s. You could predict its shape days in advance. 3I Atlas was different. The tail showed a subtle but consistent drift, a lateral displacement that suggested the gas and dust weren't streaming purely away from the sun. Instead, they were bending. Not much. Just enough to be measurable. Just enough to be wrong. Tanaka ran the numbers 3 times. She checked the solar wind data from NASA's Deep Space Climate Observatory, positioned at the lone Lagrange point between Earth and Sun. Wind speed, nominal. Particle density, slightly below average. Magnetic field orientation, stable. Nothing in the solar environment explained the drift. She sent an email to her supervisor at 11:34 p.m. local time. Subject line: possible tail anomaly in 3I. Recommend follow-up. The response came 6 hours later. Interesting. But probably just low sonar. Let's wait for better seeing conditions. Whoa. Nan. Signal to noise ratio dot. The eternal excuse. Now. But Tanaka kept watching. By the evening of January 5th, she'd pulled spectroscopic data from the European Southern Observatory's Very Large Telescope in Chile. The Vela-T had captured a mid-resolution spectrum of 3I Atlas 2 nights earlier, and the results were still being processed when Tanaka requested early access through a data-sharing agreement. What she found made her pause. There was an uptick in ionized carbon, specifically the CEI emission line at 158 micrometers. Not a huge spike, but measurable and unexplained. Ionized carbon, in a comet's coma, typically comes from solar ultraviolet radiation stripping electrons off carbon monoxide or carbon dioxide molecules. The process is well understood. The intensity correlates directly with the comet's distance from the sun and the solar wind strength. But 3I Atlas was moving away from the sun at this point, not toward it. It had reached perihelion, its closest approach, back on December 29, 2024, at a distance of 1.04 astronomical units. Since then, it had been steadily receding. The solar flux should have been weakening. The ionization should have been dropping. Instead, it was rising. Tanaka cross-referenced the data with archived observations from other interstellar visitors. Oumuamua, the first confirmed interstellar object, had been too faint and too fast for detailed spectroscopy. Twai Borisov had shown normal volatile composition, water, carbon monoxide, ammonia, all consistent with comets from our own Oort cloud. 3I Atlas was starting to look like an outlier. She wasn't alone in noticing. By January 6th, a small cluster of researchers across 3 continents had flagged similar anomalies. Dr. Ivy Loeb at Harvard posted a preprint on Arxiv titled Anomalous Ionization in Interstellar Object 3I Atlas, Natural Variability or Exotic Chemistry. The paper was careful, speculative, and loaded with caveats. But it asked the question no one wanted to ask out loud. What if the volatile composition of this object doesn't match anything we've seen before? The skeptics moved quickly. Dr. Elena Marquez, a comet dynamics specialist at the Jet Propulsion Laboratory, published a rebuttal within 24 hours. She argued that the ionization spike could easily be explained by localized outgassing. A jet of subsurface material suddenly exposed to sunlight, releasing a burst of volatiles. It had happened before. Comet 67P, Churyumov-Gerasimenko, visited by the Rosetta mission, had shown similar behavior. Jets, bursts, asymmetric plumes. Nothing exotic, just comets being comets. But Marquez's model required a specific geometry. The outgassing jet would have to be oriented almost perpendicular to the sun's direction to produce the observed tail drift. And it would have to be sustained for at least 3 days, far longer than typical comet jets, which usually last hours at most. Tanaka ran the simulation. The jet model worked. Barely. But it required parameters at the edge of plausibility. A rotating nucleus with an active region covering less than 2% of the surface. A rotation period of exactly 14.7 hours. A volatile mix, rich in carbon monoxide ice, which sublimates at lower temperatures than water ice. It was possible. But it felt forced. And there was another problem. The tail drift wasn't random. When Tanaka plotted the tail's position over 72 hours, she saw a pattern. A slow arcing curve that suggested the drift was accelerating. Not linearly, but smoothly. Almost deliberately. She didn't use that word in her notes. Deliberately. It was too loaded. Too dangerous. The kind of word that got you labeled a crank or a sensationalist. But she thought it. Because the alternative explanations were running out. On the evening of January 5th, as the Mauna Kea observatories prepared for another night of tracking, Tanaka added a note to her observation log. Tail geometry inconsistent with solar models. Ionization rising during recession phase. Recommend high cadence monitoring. Winaholi. Punchinan, shakedown. She hit send. 3,000 miles away, in a windowless office at NASA's Goddard Space Flight Center, Dr. Samir Patel read the report and frowned. He'd been tracking interstellar objects since Oumuamua's chaotic flyby in 2017. He'd written the protocols. He'd fought for the funding. He'd argued with skeptics and believers alike. And he'd learned one thing: when something doesn't fit the models, it's usually the models that are wrong. But sometimes, rarely, dangerously, it's the object. Patel forwarded Tanaka's report to the Interstellar Object Working Group, a loose coalition of astronomers, physicists, and mission planners scattered across NASA, SA, and half a dozen universities. He added a single line at the top: "We need more data, and we need it before the visibility window closes." Because the clock was already ticking. In 39 days, 3 Atlas would pass behind the sun from Earth's perspective, entering a weeks-long observation blackout. The big telescopes would lose line of sight. The data stream would go dark. And whatever was happening out there, whatever was causing the drift, the ionization, the geometry that didn't quite make sense, would continue. Unseen, unmonitored, unresolved. Tanaka stared at her screen, at the stacked images showing the faint smudge of light 29 million kilometers away. She thought about the words she hadn't written, the questions she hadn't asked, and she wondered if anyone else was noticing the same thing she was: that the tail wasn't just drifting. It was moving, like something was pushing it. Chapter 2. January 6th. Solar wind out of sinkhole. The solar wind should have been the answer. For decades, it had been the default explanation for almost every comet tail anomaly. Plasma streams from the sun's corona, accelerated to millions of kilometers per hour, colliding with the fragile comets of icy visitors, and sculpting their tails into the classic teardrop shapes we see in textbooks. The physics is elegant. The math is reliable. The predictions hold. Until they don't. On January 6, 2025, at 14:22 UTC, NASA's Advanced Composition Explorer, ATIS, detected a sudden lull in the solar wind. The spacecraft, stationed at the Lone Lagrange point, 1.5 million kilometers sunward of Earth, continuously monitors the stream of charged particles flowing outward from the sun. Its instruments measure proton density, velocity, temperature, and magnetic field strength in real time. The data that morning showed a drop, not a collapse, not a shock wave, just a gentle, sustained decrease in proton flux. The kind of quiet spell that happens a few times each solar cycle, when a coronal hole rotates away from Earth's direction and the high-speed streams dissipate. Wind velocity, down from 480 kilometers per second to 390. Proton density, down from 12 particles per cubic centimeter to 7. Magnetic field, weakening by 18%. For 3 Atlas, positioned 29 million kilometers beyond Earth's orbit, this should have been good news. A weaker solar wind meant less pressure on the tail, less ionization, a more stable, predictable geometry. But that's not what happened. Dr. Lena Kovacs, a heliophysics researcher at the European Space Agency's Space Weather Coordination Center in Brussels, was the first to notice the mismatch. She'd been tracking 3I Atlas as part of a broader study on how interstellar objects interact with our sun's plasma environment. The physics should have been straightforward. Object enters solar system, solar wind pushes tail, object leaves, tail fades. Simple. Betty went down and chimes and by the Except 3I Atlas wasn't following the script. Kovacs pulled the VALA data, the Very Large Array in New Mexico, a collection of 27 radio dishes operating in coordinated formation. The VALA had been tasked with mapping the object's radio emission, specifically looking for signatures of charged particles interacting with dust grains in the tail. The scatter patterns didn't make sense. In a normal comet tail, radio emissions follow a predictable gradient T, strongest near the nucleus, where fresh volatiles sublimate and ionize, gradually weakening with distance as the ions disperse and recombine. The emission maps should look like an elongated teardrop, brightest at the head, fading smoothly toward the tail's end. But the VALA data showed something else. There was a bulge in the emission pattern, offset from the nucleus by roughly 40,000 kilometers. A localized brightening, as if something in the tail was generating extra ionization, or as if an external source was pumping energy into the plasma. Kovacs ran the numbers. She modeled the solar wind pressure at 3A Atlas's position, factoring in the lull detected by ACE. She simulated how the weakened wind should reshape the tail over a 12-hour period. The model predicted a relaxation. The tail should have spread out slightly, becoming broader and less sharply defined as the driving pressure eased. Instead, the tail was bending. Not spreading. Not relaxing. Bending. As if something else was pushing it. She sent her findings to Dr. Samir Patel at Goddard, along with a carefully worded note. Solar wind environment inconsistent with observed tail dynamics. Possible external perturbation or localized energy source. Recommend cross-check with SOHO and Parker solar probe data. Well, Patel didn't wait. He pulled the SOHO archive, the Solar and Heliospheric Observatory, a joint NASA-ESA mission that had been watching the sun continuously since 1995. SOHO's LASCO coronagraph images showed the sun's outer atmosphere in exquisite detail, tracking coronal mass ejections and solar wind structures. Nothing unusual. No surprise flares. No unexpected ejections aimed anywhere near 3I Atlas's trajectory. He checked Parker's solar probe, NASA's daring mission that had been diving closer to the sun than any spacecraft in history. Parker had passed within 10 million kilometers of the solar surface just 2 weeks earlier, sampling the solar wind at its source. The data was clean. The wind was behaving normally, which meant the problem wasn't the sun. It was the object. By the afternoon of January 6th, a growing unease had settled over the small community of researchers tracking 3 Atlas. The anomalies were piling up. The tail drift. The ionization spike. The radio bulge. And now this. A tail geometry that didn't respond to the solar wind the way it should. Dr. Elena Marquez at JPL remained skeptical. She'd seen too many false alarms. Too many anomalies that turned out to be instrumental artifacts or misunderstood physics. She fired off an email to the working group. Before we start invoking exotic mechanisms, let's remember Occam's razor. The simplest explanation is usually correct. We're probably looking at a combination of outgassing jets and measurement uncertainty. Let's not jump to conclusions. But Patel wasn't convinced. He'd been in this field long enough to know when something felt wrong. And this felt wrong. He scheduled an emergency teleconference for January 7th, inviting 24 researchers from across the globe. The agenda was simple. What the hell is going on with 3I Atlas? Meanwhile, in a small office at the University of Arizona's Lunar and Planetary Laboratory, graduate student Marcus Chen was working late. He'd been assigned to process imaging data from the Catalina Sky Survey, a NASA-funded program that tracks near-Earth asteroids and comets. Chen wasn't part of the 3I Atlas team. He wasn't even supposed to be looking at it. But he'd heard the chatter, the rumors, the quiet speculation spreading through the astronomy forums. So he pulled the raw imaging files from January 5th and 6th. And he did something most researchers don't bother with. He looked at the individual frames, not just the stacked composites. What he saw made him sit up straight. In 3 separate frames, taken 40 minutes apart, the tail's morphology changed. Not gradually, not smoothly, but in discrete jumps. Like someone flipping a switch. Frame 1. Tail at position, angle 287 degrees. Frame 2. Tail at 284 degrees. Frame 3. Tail at 279 degrees. 8 degrees of motion in 80 minutes. Chen knew enough about comet dynamics to know that wasn't normal. Tails don't pivot that fast unless something dramatic happens. A sudden burst of outgassing. A fragmentation event. A collision with debris. But there was no brightness surge. No expanding cloud of fragments. No signs of violence. Just a tail that moved. He saved the frames, wrote up a quick analysis, and posted it to the Minor Planet mailing list. TAN Informal Clearinghouse for observations of comets, asteroids, and other small bodies. The post went live at 11:47 p.m. Mountain Time. By sunrise, 43 researchers had downloaded the data. By noon, the teleconference had been moved up to January 7th at ADCO-ATC. And by evening, a new term was starting to circulate in private emails and Slack channels. Anomalous tail dynamics. Not unusual. Not unexpected. Anomalous. The kind of word you use when you don't want to say what you're really thinking. Because what Chen's frames suggested, what Kovacs's radio data implied, what Tanaka's ionization curves hinted at, was something that shouldn't be possible. The tail wasn't just responding to the solar wind. It was responding to something else. Something closer. Something inside the object itself. Or, and this was the thought no one wanted to voice, something controlling the object. Patel sat in his office, staring at the cascade of data streaming across 3 monitors. Solar wind. Nominal. Tail geometry. Impossible. Chemistry. Wrong. Timing. Worse. He thought about Oumuamua, the cigar-shaped visitor that had baffled scientists in 2017 with its strange acceleration, its lack of a visible tail, its refusal to fit neatly into any category. Asteroid? Comet? Something else? The debate had raged for years. Some scientists proposed it was a nitrogen iceberg from a Pluto-like exoplanet. Others suggested it was a hydrogen ice flake, puffed up and light enough to be pushed by sunlight alone. Avi Loeb had suggested it might be artificial. A light sail. A probe. A piece of extraterrestrial technology. He'd been ridiculed. Marginalized. Dismissed as a publicity seeker. But Patel remembered something Loeb had said in an interview. The universe doesn't care about our categories. If we only look for what we expect to find, we'll miss what's actually there. Damn. Patel didn't believe 3 Atlas was a spacecraft. But he was starting to believe it wasn't just a comet. And that scared him more than he wanted to admit. Because if it wasn't a comet, if it was something we'd never seen before, something that didn't fit our models or our physics or our understanding of how interstellar objects behave, then the rules had changed, and we were playing a game we didn't know how to win. He pulled up the observation schedule for the next 2 weeks. The window was narrowing. Soon, the sun's glare would make detailed observations impossible. They had days, maybe a week, and then 3I Atlas would vanish, taking its secrets with it. Chapter 3, January 7th. The Tail That Bent Backwards. The teleconference started at exactly 8:00 UTC time. 26 faces filled the Zoom grid. Astronomers, physicists, mission planners. Some sitting in sunlit offices, coffee in hand. Others joining from darkened observatories between imaging runs. A few dialing in from home, children's voices audible in the background. Dr. Samir Patel spoke first. Thank you all for joining on short notice. I know we're all stretched thin right now, but we need to consolidate what we know about 3E Atlas before the observation window closes. Dr. Tanaka, let's start with you. Walk us through what you've been seeing. Yuki Tanaka shared her screen. A series of images appeared, showing the faint smudge of 3 Atlas against a star field. Arrows and annotations marked the tail's position over 5 consecutive nights. The tail has been drifting laterally since January 5th, she began. Initially, I thought it was calibration error, but the drift is consistent across multiple instruments, Pan-STARRS, VELT, and now the Catalina Sky Survey. The position angle has shifted by 11 degrees over 72 hours. Someone unmuted. That's fast. Too fast, Tanaka agreed. For comparison, Tui Borisov's tail varied by less than 3 degrees over an entire month, and that was during perihelion, when outgassing was at its peak. Dr. Elena Marquez chimed in. But 3I Atlas is post-perihelion now, right? Moving away from the sun. If there's active outgassing, we should see it slowing down, not speeding up. Exactly. Tanaka advanced to the next slide. A spectroscopic plot, spiked with emission lines. And yet, the ionization is increasing. Specifically, ionized carbon at 158 micrometers. The intensity has risen by 24% since January 3rd. Silence. Then Lena Kovacs spoke, her accent faint but precise. And the solar wind has been decreasing. ACE data shows a sustained lull starting January 6th. The proton flux is down. The magnetic field is weaker. If anything, we should be seeing less ionization, not more. Patel leaned forward. So we have a tail that's moving faster than it should, ionization that's rising when it should be falling, and a solar wind that can't explain either. Does anyone have a model that fits all three? Marcus Chen, the graduate student from Arizona, unmuted hesitantly. I might have something, but it's speculative. Everything about this object is speculative at this point, Patel said. Go ahead. Chen shared a simulation he'd run overnight. A rotating nucleus with multiple active regions, jets of sublimating ice firing in different directions. If the rotation was fast enough, and the jets were positioned asymmetrically, they could create a wobbling tail that looked like lateral drift. It's called the pinwheel model, Chen explained. We've seen it in a few comets before. Comet Encke showed something similar in 2013. If the nucleus is spinning every 6 to 8 hours, and the jets are offset from the rotation axis, you get this kind of motion. What exactly? Marques nodded approvingly. That's plausible. Have you calculated the required rotation period? Yeah. It works if the spin is between 6.4 and 7.1 hours. Anything slower, and the tail drift doesn't match. Anything faster, and we'd see periodic brightness variations that we're not observing. Tanaka zoomed in on her light curve data, a plot of the object's brightness over time. It was almost flat. No obvious periodicity. No flickering. That's a problem, she said quietly. If the nucleus is spinning that fast, we should see it in the photometry, active regions rotating in and out of sunlight. Brightness changes every few hours, but we don't. Chen frowned. Unless the surface is unusually uniform, or the jets are distributed evenly. Both unlikely, Marques countered. Comets are messy, irregular shapes, patchy surfaces. We've never seen a comet with perfectly balanced outgassing. The grid fell silent again. Then Avi Loeb unmuted. He'd been listening without comment for 20 minutes. Perhaps we're thinking about this wrong, he said, his voice calm. We keep trying to fit 3E Atlas into the category of comet. But what if it's not a comet? What if it's something else? Marques sighed. Avi, we've been over this. Just because we don't understand something immediately doesn't mean it's artificial. I'm not saying it's artificial, Loeb replied. I'm saying it might not be a typical icy body. What if it's a hybrid, part ice, part rock, or a rubble pile with pockets of volatiles scattered throughout? That could produce the asymmetric outgassing without requiring a fast rotation. Kovacs jumped in. But that still doesn't explain the ionization increase. If the solar wind is weakening, where's the energy coming from? Internal, someone suggested. A voice from the lower right corner of the grid. Dr. Hiroshi Yamamoto, a planetary scientist from JAXA. What if there's a heat source inside the object? Radioactive decay, tidal heating from a past encounter, chemical reactions. Patel considered it. Radioactive decay is too slow. Tidal heating requires a recent close pass, which we have no evidence for. Chemical reactions? Maybe. But we'd need a pretty exotic mix of materials. Not that exotic, Yamamoto countered. Some meteorites contain perchlorates, chlorine compounds that release oxygen when heated. If 3 Atlas has a perchlorate-rich interior, and cracks are forming as it rotates, exposing fresh material to sunlight, then you'd get bursts of oxygen, Tanaka finished, which could ionize carbon monoxide in the coma, raising the CNI levels. It was a reach, but it was possible. The conversation shifted, morphed, fragmented into side debates. Someone proposed magnetic field interactions. Another suggested micrometeorite impacts. A third floated the idea of resonant absorption of solar radiation at specific wavelengths. Theories piled on theories. But none of them fit everything. And then, at 9:14 UTC, an email arrived in Patel's inbox. The subject line read, Urgent 3I Atlas tail reversal event. He opened it mid-discussion. His face went still. Excuse me, he interrupted. We need to look at this. He shared the email on screen. It was from Dr. Sofia Reyes, an astronomer at the Cerro Tololo Inter-American Observatory in Chile. She'd been conducting a 9-hour observation block on 3E Atlas, tracking it continuously through the night. The message was short. Tail reverse direction between 2:0 and 11:0 UTC. Confirmed across multiple filters. Not an artifact. Tail flipped. Uploading data now. Patel opened the attached images. The first frame, time-stamped 2:13 UEC, showed the tail extending at position angle 276 degrees, roughly southwest, away from the sun. The second frame, 9 hours later at 11:09 UEC, showed the tail at 94 degrees, 182 degrees of rotation. A complete reversal. The grid erupted. That's impossible. Check the calibration. Is the timestamp correct? There's no way a tail moves that fast. But Sofia Reyes was already in the chat, typing rapidly. Calibration verified. Timestamp correct. Cross-checked with 2 other telescopes. The tail flipped. Tanaka pulled up her own data. She'd been tracking the object from Hawaii, but clouds had blocked her view for part of the night. She had frames at 150 UTC and 1240 UTC. The positions matched Reyes's data. The tail had reversed. Dr. Marquez's skepticism cracked. I don't have a model for this. Chen spoke up, his voice uncertain. What if the object fragmented? If the nucleus broke apart, you could get a sudden release of volatiles that... No brightness surge, Tanaka interrupted. No expanding debris cloud. The nucleus looks intact. Kovacs was scrolling through the VLA data. The radio emissions spiked during the same window, doubled in intensity between 4 and 8:0 UTC, then dropped back to baseline. Patel felt something cold settle in his chest. He'd spent 30 years studying comets, asteroids, and interstellar visitors. He'd seen chaotic tumbling. He'd seen fragmentation events. He'd seen outgassing jets that defied prediction. But he'd never seen a tail flip direction in 9 hours. Not without a cause. Loeb spoke again, quieter now. We need to consider the possibility that this object is not behaving passively. That something about its structure, its composition, its internal dynamics, is actively influencing its behavior. Actively? Mackay echoed. Avi, that's not technology, Loeb clarified. I'm not saying that, but perhaps a configuration we've never encountered. A resonance, a feedback loop. Something that makes it respond to solar input in a non-linear way. Someone whispered a word that most of the group had been avoiding. Stabilized. Patel closed his eyes. Stabilized implied control. Control implied intent. Intent implied. He didn't finish the thought. We need continuous monitoring, he said finally. Every telescope we can get. High cadence. Full spectrum. If this thing is going to keep surprising us, I want to know the moment it happens. The group agreed. Observation requests were filed. Time was allocated. Arrays were coordinated. But everyone on that call knew the truth. They were running out of time. In 27 days, 3I Atlas would slip behind the sun. And whatever was happening out there, whatever was causing a tail to flip, ionization to spike, and radio emissions to pulse, would continue. Unseen de Torsto. This is not science fiction. This is January 2025. And the universe is speaking in a language we're only beginning to understand. Chapter 4, January 9th, GWST. The James Webb Space Telescope wasn't designed to study comets. It was built to peer into the ancient universe, to capture the first galaxies forming in the cosmic dawn, to dissect the atmospheres of distant exoplanets, and unravel the chemistry of star birth in nebulae billions of light years away. Pointing it at a faint, unpredictable interstellar visitor just 29 million kilometers from Earth felt, to some mission planners, like using a Formula One car to deliver groceries. But on January 9th, 2025, a small allocation of observing time, granted through an emergency director's discretionary program, was redirected toward 3 Atlas. The observation window was narrow. Just 43 minutes. Enough for a single mid-infrared snapshot using the MIRI instrument. The mid-infrared instrument. Sensitive to wavelengths between 5 and 28 micrometers. Thermal radiation. Heat signatures. The kind of light that reveals temperature differences invisible to optical telescopes. The data arrived at the Space Telescope Science Institute in Baltimore at 1734 UTC. Dr. Claudia Monroe, a planetary scientist specializing in small-body thermal modeling, was the first to open the file. She'd submitted the observing proposal 4 days earlier, arguing that JWST's sensitivity could resolve thermal heterogeneity on the nucleus. Temperature variations that might explain the anomalous outgassing. What she saw on her screen made her lean back in her chair. Oh, that's weird. The nucleus of 3 Atlas appeared as a faint blob, barely resolved even at JWST's remarkable resolution. That was expected. The object was small, estimated at 2 to 3 kilometers across, and far away. But the thermal map was anything but uniform. Most comets, when viewed in infrared, show a predictable pattern. The sun-facing side is hotter. The shadowed side is colder. If the comet is rotating, you see a smooth gradient, like a slowly turning light bulb. 3 Atlas showed a hotspot, a localized region on the sunward hemisphere, roughly 300 meters across, glowing 15 to 20 Kelvin hotter than the surrounding surface. 15 to 20 degrees doesn't sound like much. But at this distance from the sun, where surface temperatures hovered around 210 Kelvin, cold enough to freeze carbon dioxide, a 20-degree anomaly was significant. Monroe ran a thermal model. If the hotspot was just a patch of darker material, like exposed rock or carbonaceous dust, it could absorb more sunlight and heat up faster than the surrounding ice. The model worked. Barely. But it required the dark patch to be perfectly positioned, facing the sun at exactly the right angle. And it required the material to have unusually low thermal inertia, heating and cooling faster than typical cometary surfaces. She tried another approach. What if the hotspot wasn't just absorbing sunlight? What if it was emitting heat? An internal source. A pocket of warm material venting through a crack in the surface. That model worked too. But it required a sustained heat source beneath the surface. Something generating energy over hours, not minutes. Monroe saved both models and sent them to Patel with a note. JWST thermal imaging shows asymmetric heating. Could be surface albedo variation. Could be subsurface venting. Either way, it's not behaving like a normal comet. Recommend follow-up. Nintendo. Patel read the email and pulled up the thermal image himself. He stared at the hotspot, a small orange bloom against the cooler blues and greens of the nucleus. He thought about the tail reversal, the ionization spike, the radio bulge, and now this. A heat source that pulsed on and off like a dimmer switch. He forwarded the data to the working group with a single line. We're building a profile of something we don't understand. By midday on January 9th, the JWST data had been shared with 24 researchers. The responses came fast. Dr. Yamamoto from JAXA proposed a thermal inertia model, suggesting the hotspot was a boulder embedded in the surface, a rocky fragment with different heating properties than the surrounding ice. Dr. Kovacs ran a magnetohydrodynamic simulation, testing whether focused solar wind particles could be channeled toward one region of the surface by a localized magnetic field. Dr. Chen suggested a combination model, a subsurface cavity filled with warm volatiles, venting intermittently through a fissure that opened and closed as the nucleus rotated. Each model had merit. Each model had problems. And none of them explained why the hotspot seemed to oscillate. Because that was the detail Monroe hadn't included in her first email. She'd been waiting to confirm it. But when she processed the JWST data at higher time resolution, extracting every available frame from the 43-minute observation window, she saw something troubling. The hotspot wasn't constant. It brightened, dimmed, brightened again, over a period of roughly 18 minutes. She ran a Fourier analysis, a mathematical technique for detecting periodic signals hidden in noisy data. The result was marginal, a faint peak in the power spectrum, suggesting a repeating cycle. She didn't trust it. The signal-to-noise ratio was too low. The observation window too short. But she couldn't ignore it either. She called Patel directly. "We might have a periodicity," she said, skipping pleasantries. "In the thermal emission, 18 to 19 minutes. I can't confirm it with this dataset alone, but, it's there," Patel finished. "It's there." Patel rubbed his eyes. He'd been awake for 16 hours, coordinating observations, reviewing data, fielding questions from NASA's Planetary Defense Coordination Office, a group suddenly very interested in an object that, technically, posed no threat to Earth. "If there's a periodicity in the thermal emission," he said slowly, "and it's not tied to the rotation, then something else is driving it," Monroe agreed. "Something internal. Or something external." They both knew what that implied. If an external source was pumping energy into 3I Atlas, if something was heating it in a rhythmic, repeating pattern, then the list of natural explanations shrank rapidly. Tidal forces required a companion object. None had been detected. Magnetic reconnection required a strong planetary magnetosphere. There was none nearby. Resonant absorption of solar radiation required a very specific geometry and composition. Possible, but unlikely. That left two options. Either 3 Atlas contained an internal mechanism, chemical, geological, or otherwise, that generated heat impulses. Or something was interacting with it. Something we couldn't see. Patel didn't voice the second option out loud. He didn't need to. Monroe was thinking the same thing. "I'm submitting a follow-up request," Monroe said. "Longer observation, full thermal mapping. If we can catch this thing over a complete rotation period, we'll know for sure." "Do it," Patel said. "But hurry. The review board meets tomorrow, and discretionary time is a knife fight right now." Windoma. He wasn't exaggerating. JWST was the most oversubscribed telescope in history. For every hour of observing time, there were 100 proposals competing. Galaxies, exoplanets, supernovae, black holes, each one scientifically compelling, each one deserving. And now a small faint interstellar comet was asking for more. The politics were brutal. Dr. Laura Hendricks, GOST Deputy Project Scientist, had already fielded 3 angry emails from researchers whose approved observations had been bumped to make room for the January 9th snapshot. One team had been waiting 18 months to observe a specific exoplanet transit. Another had lost a critical window to study a distant supernova. Both were furious. "This better be worth it," Hendricks muttered to herself, reviewing Monroe's follow-up request. She read the justification, looked at the thermal map, Daiwanzi, frowned at the oscillation data. She'd been in this job long enough to know when something felt off. And this felt off. She approved the request. But she added a note, "One more shot. If the follow-up doesn't yield actionable science, no further discretionary time will be granted." Monroe got the notification at 1922 UTC. 72 hours. That's how long she had to wait for the next observation window. She marked it on her calendar. January 12th. 80 UEC tot. She didn't know it yet, but that would be the same day the tail flipped. The same day the radio emission spiked. The same day a graduate student at Green Bank Observatory would notice a faint, repeating pulse buried in the noise. But for now, Monroe sat in her office, staring at the thermal map, at the orange hotspot that shouldn't exist. And she thought about something her advisor had told her years ago, when she was just starting her PhD. The universe doesn't owe us explanations. Sometimes it just shows us something new, and we have to decide whether to look away or lean in. And Monroe had always leaned in, even when it scared her. Especially when it scared her. Because that's where the discoveries lived. In the uncomfortable spaces between what we know and what we don't. And 3I Atlas was becoming the most uncomfortable space she'd ever encountered. Somewhere out there, 29 million kilometers away, a small, dark object was tumbling through the void. And somewhere inside it, or on it, or around it, something was generating heat, Impulses. Like a heartbeat. Chapter 5. January 11th. Chemistry that shouldn't exist. The spectroscopy data from the Apache Point Observatory arrived late on January 11th, just after midnight Mountain Time. Dr. Mylene Park had been running the 3.5-meter telescope remotely from her home office in Santa Fe, guiding the instrument through a carefully planned sequence targeting 3A Atlas. She'd been allocated 4 hours, a luxury in the world of shared telescope time, and she'd used every minute to capture high-resolution spectra of the object's coma. The goal was simple: identify what the comet was made of. Break down the light into its component wavelengths, match the emission and absorption lines to known molecules, and build a chemical inventory. Comets are time capsules, frozen relics from the formation of planetary systems. By studying their composition, we learn about the raw materials that built worlds. Oxygen, carbon, nitrogen, hydrogen. Water, carbon monoxide, ammonia, methane, the basic building blocks of chemistry. Most comets follow a predictable recipe. They're dominated by water ice, with carbon monoxide making up 5 to 10% of the volatiles. Trace amounts of methanol, formaldehyde, hydrogen cyanide. The ratios vary slightly, but the ingredients are consistent. Borisov had fit the pattern perfectly. When it passed through our solar system in 2019, spectrographic analysis showed it was indistinguishable from comets born in our own Oort cloud. Same chemistry, same ratios, same cosmic recipe. 3A Atlas was different. Park stared at the spectrum on her screen, running through it line by line. Water. Water, present, but weaker than expected. Carbon monoxide? Strong, very strong. Almost 30% of the total volatile mix. Ammonia? Barely detectable. And then, she saw it. A sharp emission line at 155.4 micrometers. Ionized carbon monoxide, caught or not. That wasn't unusual by itself. Solar ultraviolet radiation ionizes Ko in most cometary comas. But the intensity was wrong. At 3 Atlas's current distance from the Sun, 1.18 astronomical units and receding, the ionization rate should have been dropping. Instead, it was spiking. Park cross-referenced the signal strength against models of solar UV flux at that distance. The ionization rate was 3 times higher than predicted. She checked the data reduction pipeline. No errors. She checked the calibration files. Clean. No. She ran the spectrum through an independent analysis package. Same result. The SU emission was real, and it was excessive. But there was something else. Another line. Fainter, but unmistakable. An emission feature at 372.6 nanometers. Ionized nickel. Nini. Toy. Park froze. Nickel emission isn't impossible in comets. It's been detected before, in trace amounts, released when dust grains ablate in the coma. Meteoritic material, tiny flecks of metal embedded in the ice, can vaporize when heated, releasing metallic atoms that fluoresce under solar UV. But the nickel emission in 3 Atlas was strong, far stronger than the trace levels seen in typical comets. And it shouldn't have been there at all, because metallic nickel requires high-temperature formation. It's a byproduct of stellar nucleosynthesis, forged in the cores of dying stars and scattered into space during supernova explosions. It's found in asteroids, in meteorites, in the iron-rich cores of differentiated planets, but not in comets. Comets are cold. They form in the outer reaches of planetary systems, where temperatures never exceed a few tens of Kelvin. They don't melt. They don't differentiate. They don't forge metal. So where did the nickel come from? Park ran through the possibilities. Maybe 3I Atlas had collided with an asteroid in its home system, embedding metal fragments in its icy matrix. That could explain a small amount of nickel. But the emission strength suggested metal made up a significant fraction of the dust, far more than a chance collision would produce. Maybe the object formed closer to its parent star, in a warmer region where metal grains could condense. But then, how did it get enough ice to produce the observed outgassing? And why was the CO ratio so high? Maybe. She stopped. There was a third possibility, one she didn't want to consider. Maybe 3 Atlas wasn't a comet. Maybe it was something else. A hybrid. A fragment of a destroyed planet. A piece of a shattered protoplanetary disk. Or something we'd never seen before. She saved the spectrum and sent it to the working group. No commentary. Just the data and a subject line. Anomalous metallic emission in 3 Atlas stored height. Ni detected at 3.8 sigma confidence. Done. The response was immediate. Dr. Yamamoto, metallic grains? Possible meteoritic contamination? Dr. Tanaka, the intensity also elevated. 2 anomalies now out. Dr. Marquet, let's not jump to conclusions. Nickel emission could be instrumental artifact, need independent confirmation. But Patel wasn't waiting for confirmation. He pulled archive data from the Stratospheric Observatory for Infrared Astronomy, SOFIA, a modified Boeing 747 carrying a 2.5-meter telescope. SOFIA had observed 3I Atlas on January 8th, before the GGUST snapshot, capturing far infrared spectra. He found what he was looking for in the archived files. A faint emission line at 63.2 micrometers. Ionized oxygen. Nothing surprising there. Oxygen emission is common in comets, produced when water molecules break apart under solar UVD. But the OU intensity was low. Much lower than it should be, given the water content inferred from optical observations. He did the math. If you compared the OUA intensity to the Kawami intensity, you got a ratio that didn't make sense. The oxygen-to-carbon ratio in 3 Atlas was inverted. There was more carbon emission than oxygen emission. But water, is the primary oxygen source in comets. If there was enough water to produce the observed O emission in optical spectra, there should be more oxygen than carbon, unless there wasn't as much water as they thought, or unless the carbon was coming from somewhere else. Patel pulled up a chemistry textbook, something he hadn't needed in years. He skimmed through chapters on interstellar ice composition, looking for scenarios where carbon-rich volatiles could dominate over water. He found one. Cold, molecular clouds. Denser regions of interstellar space, where starlight is blocked, temperatures drop to 10 Kelvin, and ice forms on dust grains in complete darkness. In those environments, carbon monoxide ice can be more abundant than water ice. But those clouds are between stars, not around them. If 3I Atlas formed in a molecular cloud before being ejected into interstellar space, its chemistry would be different. Alien. Not by origin, but by environment. It would be a relic from the space between worlds. Patel sent his findings to the group, and he added a single line. We need to consider the possibility that this object didn't form in a planetary system. The chat erupted. Dr. Monroe, you're saying it formed in interstellar space before captured by a star. Patel, I'm saying it's chemically distinct from every other comet we've studied. If it formed in a molecular cloud and was ejected during the collapse that formed its host star. Dr. Loeb, then it's older than planets. Older than stars. A pristine sample of the primordial interstellar medium. Dr. Marquez, that's a hell of a claim, Samir. We need a lot more data before we... But the conversation was interrupted by a notification. An automated alert from the Green Bank Observatory. A radio pulse. Repeating. Low confidence. 28-minute period. Patel's screen refreshed. He stared at the alert. 28 minutes. Not 18. Not 31. 28. A new number. A new periodicity. Or the same signal, refined. He didn't know which possibility scared him more. Because if the periodicities were related, if the thermal pulse at 18 minutes and the radio pulse at 28 minutes were harmonics of the same underlying mechanism, then 3 Atlas wasn't just outgassing. It was oscillating, like a machine, or a clock, or something waiting. Chapter 6. January 12th. The Flip. January 12th, 2025, began like any other day in the small community of astronomers tracking 3 Atlas. Telescopes around the world resumed observations as night fell across their respective longitudes. In Chile, the Very Large Telescope locked onto the faint object at twilight. In Hawaii, Pan-STARRS began a new imaging sequence. In Arizona, the Large Binocular Telescope allocated 2 hours for high-resolution spectroscopy. No one expected the day to be historic. But at 3:47 UTC, something extraordinary happened. The tail of 3 Atlas flipped completely. In less than 9 hours, the delicate streamer of ionized gas and dust, which had been pointing consistently away from the sun for days, reversed direction by more than 160 degrees. Dr. Sofia Reyes, observing from Cerro Tululo in Chile, noticed it first. She'd been tracking the object continuously since 2:00 UTC, capturing frames every 12 minutes and 3 optical filters. The data pipeline processed the images in near real time, displaying them on her monitor as they came in. At 2:13 UTC, the tail was at position angle 276 degrees southwest, trailing behind the nucleus as expected. At 5:42 UTC, the tail was at 312 degrees northwest, bending. At 8:31 UTC, the tail was at 18 degrees northeast, rotating. By 11:09 UTC, the tail was at 94 degrees east, nearly perpendicular to its original orientation. Reyes checked the astrometry. The telescope's pointing was accurate. The world coordinate system was calibrated. The timestamps were correct. The tail had moved. She pulled up theoretical models, running through scenarios in her head. Sudden fragmentation? No brightness surge. Massive outgassing burst? No expanding halo. Collision with debris? No secondary objects detected. She grabbed her phone and called Patel directly. Samir, you need to see this. 3 minutes later, Patel was staring at the image sequence on his laptop, still in his pajamas, coffee forgotten on the kitchen counter. This is confirmed? He asked. Triple-checked, Reyes said. And I'm not the only one seeing it. Pan-STARRS caught the same motion. So did the Catalina Sky Survey. Patel pulled up the radio data from the Very Large Array. The Velia had been monitoring 3 Atlas overnight, tracking plasma emission in the tail. The radio intensity had spiked. At 4:17 UTC, the emission was at baseline, roughly 1.4 millijanskis at 6 JUTSDAT. By 7:50 UTC, it had jumped to 4.7 millijanskis, a 3-fold increase in 3.5 hours. Then, just as suddenly, it dropped. By 10:30 UTC, the emission was back to baseline. Patel felt a chill run down his spine. He'd seen comets do strange things. He'd seen tails twist, bifurcate, fade, and brighten. He'd seen jets fire in unpredictable directions. He'd seen fragmentation events that turned single objects into clouds of debris. But he'd never seen a tail flip. Not like this. Not this fast. Not without a visible cause. He opened the working group chat and typed, "Emergency meeting. Whatever. 14. Euro OTCTO. Everyone who can attend, please do. We have a situation. Nebnida. Kenfernwedda. Wantamount for DTMETC." By 14:00 UTC, 32 researchers had joined the video call. The usual pleasantries were skipped. Patel shared the imaging sequence immediately. The grid went silent. Then Dr. Kovac spoke, her voice tight. The solar wind is still in a lull. ACE data shows stable conditions. Low particle flux. Weak magnetic field. There's nothing in the space weather that explains this. Dr. Chen pulled up his pinwheel model, the rotating jet scenario he'd proposed days earlier. If the nucleus is spinning, and a jet suddenly activated on the opposite side, the timescale doesn't work, Tanaka interrupted. To flip the tail this fast, you'd need a jet powerful enough to overwhelm the solar wind entirely. That requires outgassing rates we haven't observed. Dr. Yamamoto chimed in. What if the object fragmented? A split nucleus could produce dual jets pointing in opposite directions. Reyes shook her head. No fragmentation signature. The nucleus is still intact, single-point source, no secondary components. Dr. Mark S., who had been skeptical from the beginning, finally sounded uncertain. I don't have a natural explanation for this, not one that fits the timeline. The silence stretched. Then Loeb spoke. We keep trying to explain this object using mechanisms we've seen before. But what if we're looking at something new? Not artificial, not technological, but a physical process we haven't encountered. Going to... Like what? Someone asked. I don't know, Loeb admitted. But the universe is full of surprises. Neutron stars, fast radio bursts, dark matter. We didn't predict any of them. We discovered them by observing first and theorizing later. Patel rubbed his temples. So what do we tell people? That we have no idea what's going on? We tell them the truth, Loeb said simply. That we're watching something unprecedented, and we're working to understand it. But Patel knew it wasn't that simple. Because 3 floors above his office, in the NASA headquarters building in Washington, D.C., administrators were starting to ask uncomfortable questions. Questions like, is this object a threat? And should the public be informed? And, most troubling, what if it's not natural? The Planetary Defense Coordination Office, BDCU, had been established in 2016 to track near-Earth objects and coordinate responses to potential impact threats. Its mandate was narrow: identify hazardous asteroids and comets, calculate collision probabilities, and develop mitigation strategies. 3 Atlas wasn't a threat. Its trajectory kept it well outside Earth's orbit. No collision was possible. But the PDO was paying attention anyway. Because if the object was exhibiting behavior that couldn't be explained by natural processes, then it fell into a different category. A category that didn't officially exist, but which had been discussed quietly in classified briefings for decades. On the afternoon of January 12th, Dr. Lindley Johnson, NASA's Planetary Defense Officer, received a call from the office of the director. The conversation lasted 7 minutes. When it ended, Johnson sat at his desk, staring at his notes. Then he picked up the phone and called Patel. Samir, we need to talk. Off the record. Patel stepped out of his office and into an empty conference room. What's going on, Lindley? The tail flip is getting attention. Higher up than you might think. Meaning? Meaning people are asking whether this is something we need to prepare for. Patel's stomach tightened. Prepare for? It's a comet, Lindley. It's 29 million kilometers away and moving away from us. I know that. But the anomalies are piling up. The chemistry, the thermal pulses, the radio emissions. And now this? A tail that flips without a cause. People are nervous. People? People? Above my pay grade. Patel exhaled slowly. What do they want? Answers, soon. And if we can't provide them, they're going to start considering alternative explanations. Alternative explanations, Patel repeated. You mean in extraterrestrial technology? I mean they're going to ask questions we're not equipped to answer. Patel leaned against the wall. Lindley, I've been studying comets for 30 years. I know how they work. I know how they die. And I know how they surprise us. But this is different. I can't explain it. Not yet. Then we need more data. Fast.ol. Because the observation window is closing. And once this thing goes behind the sun, we'll have nothing. I know. And Samir? Yeah? If this turns out to be something other, you need to be ready for what comes next. The call ended. Patel stood in the empty conference room, listening to the hum of the HVAC system. Outside, the January sun was setting. The sky was turning orange, then red, then purple. And somewhere out there, 29 million kilometers away, a small dark object was tumbling through the void. Its tail had flipped. Its chemistry was wrong. Its thermal signature pulsed. And in 17 days, it would vanish behind the sun, taking its secrets with it. Unless they could solve the puzzle first. Patel returned to his office and pulled up the observation schedule. He started making calls, requesting emergency telescope time, coordinating with international partners. drafting proposals, because the universe had just handed humanity a mystery, and walking away wasn't an option. This is not science fiction. This is January 2025. And the clock is ticking. Chapter 7, January 14th, The Periodicity Problem. The discovery came from an unexpected source. Not from a senior researcher with decades of experience. Not from one of the big telescopes with cutting-edge instruments. It came from a 24-year-old graduate student named Rachel Kim, working the night shift at the Green Bank Observatory in West Virginia. Green Bank operates the world's largest fully steerable radio telescope, a 100-meter dish nestled in the National Radio Quiet Zone, a region where radio transmissions are strictly limited to minimize interference. It's one of the quietest places on Earth, electronically speaking. Perfect for listening to the faint whispers of the cosmos. On the night of January 14th, Kim was running a routine monitoring program, sweeping the telescope across a list of targets including pulsars, masers, and a handful of solar system objects. 3. Atlas was on the list. A low-priority target. 10 minutes of integration time at L-band frequencies, 1 to 2 GHz, just enough to check for any radio emission from ionized gas in the tail. She didn't expect to find anything. Comets are usually radio quiet unless they're producing massive outgassing events or interacting with a planetary magnetosphere. But when the data came in, she saw something odd. A faint, repeating pulse. It wasn't strong. Barely above the noise floor. The kind of signal that would normally be dismissed as interference. A passing satellite, a glitch in the electronics, a car driving past the fence with a faulty alternator. But Kim had been trained to be thorough. She checked the flagging logs. No known satellites were in the beam. No local interference reported. The telescope's pointing was stable. She reprocessed the data, applying a tighter filter to remove noise. The pulse was still there. And it was periodic. Every 31.2 minutes, a faint brightening in the radio emission, lasting about 40 seconds, then fading back to baseline. Kim stared at the screen, her heart rate picking up. Periodic signals in astronomy usually mean one of three things: rotation, orbit, or oscillation. Pulsars rotate. Binary stars orbit. Stars oscillate. But comets don't pulse. She ran a periodogram analysis, a mathematical tool for detecting hidden periodicities in time series data. The result came back with a strong peak at 31.2 minutes. Confidence level, 78%. Watch 2. Not definitive, but not random either. She saved the data and sent it to the observatory's director with a note. Possible periodic emission detected in 3A Atlas. Los NR. Requesting follow-up observation. The response came an hour later. Interesting. Forward to the Interstellar Object Working Group. Copy Patel at Goddard. By dawn on January 15th, Kim's data was being dissected by a dozen researchers across 3 continents. Dr. Tanaka pulled up her optical light curve data, looking for a corresponding periodicity in the brightness. Nothing. The object's optical luminosity was steady. Dr. Kovacs checked the Valley logs. No obvious periodicity in the radio continuum emission. But the Vale observations had been intermittent, not continuous. If the pulse only lasted 40 seconds every half hour, it could easily have been missed. Dr. Monroe reviewed the GWST thermal data. The 18-minute oscillation she'd tentatively identified didn't match Kim's 31.2-minute period. But it was close enough to be related. Maybe a harmonic. Maybe a beat frequency. Maybe 2 separate processes interfering with each other. Patel did the math. If you took the 31.2-minute period and divided it by 1.73, you got 18 minutes. Not exact, but close. A ratio of roughly 1.7 to. In physics, simple ratios often hint at resonance. Coupled oscillators. Systems locked into harmonic relationships by feedback mechanisms. He pulled up examples. Jupiter's moons, Io, Europa, and Ganymede, orbit in a 1-4 resonance, their gravitational pulls synchronized. Saturn's rings show resonant gaps carved by moonlets. Even the human heart exhibits coupled oscillations between atrial and ventricular contractions. But comets? Comets don't have coupled systems. They're just dirty snowballs. They rotate. They sublimate. They fragment. They don't oscillate in harmonic modes. Unless something was making them oscillate. Patel sent a message to the working group. 2 periodicities detected. 18 minutes, thermal, and 31 minutes, radio. Possible harmonic relationship. Need continuous monitoring to confirm. The response from Dr. Marquez was immediate. We're seeing patterns because we're looking for them. Human brains are wired to find order in chaos. Let's not overinterpret low-confidence signals. She had a point. Pareidolia, the tendency to see faces in clouds, or patterns in randomness, was a well-known cognitive bias. Astronomers had fallen victim to it before. The infamous wow signal from 1977, a brief radio burst that was never detected again. The phosphine detection in Venus's atmosphere, later challenged by reanalysis. The dimming of Tabby's star, which sparked speculation about alien megastructures before being attributed to dust clouds. Science required skepticism. Extraordinary claims required extraordinary evidence. But Patel couldn't shake the feeling that this was different, because the anomalies weren't isolated. They were accumulating. The tail flip. The chemistry. The thermal hotspot. That's the radio pulse. Each one, taken alone, could be explained away. But together they painted a picture of an object that was behaving in a coordinated, structured way. He reached out to Dr. Helen Zhao, a signal processing expert at night, who specialized in detecting weak periodic signals in noisy data. If anyone could confirm or refute Kim's findings, it was Zhao. She agreed to analyze the Green Bank data independently. 48 hours later, she sent her results. Periodicity confirmed. 31.24 8.8 minutes. Confidence. 89%. Signal consistent across multiple observation epochs. Not instrumental artifact. When Devi Karno Kamichi. Patel felt his pulse quicken. 89% confidence. That was high enough to be taken seriously. He forwarded Zhao's analysis to the working group. This time, even Marquez didn't object. But she added a note. Confirmed periodicity means we have a phenomenon to explain. Not evidence of anything specific. Could be a rotating nucleus with an asymmetric jet. Could be precession. Could be librational oscillation. Let's not jump to conclusions. Nensenjai. Loeb responded. Agreed. But we should also consider the possibility that this is a natural process we've never observed before. Something unique to interstellar objects. Or something rare enough that we've never caught it until now. Yamamoto added, if the periodicity is tied to rotation, we need to measure the rotation period directly. Optical light curve, radar echo, something definitive. But there was a problem. Radar observations required the object to be close, within a few million kilometers. 3I Atlas was too far. And it was getting farther every day. Optical light curve measurements required a detectable brightness variation, DOS. But 3I Atlas was faint, and its light curve was nearly flat. If the nucleus was rotating, it was doing so without producing obvious brightness changes, which left them with indirect evidence. Periodicities in thermal emission and radio pulses. Hints. Shadows. Not proof. Patel sat back in his chair, staring at the growing list of observations. Somewhere out there, 3 Atlas was spinning, or oscillating, or pulsing, in a rhythm that nature had somehow produced, or that nature was being told to produce. He didn't believe in alien spacecraft. He didn't believe in panspermia probes or interstellar messengers. But he did believe in the scientific method. And the method demanded one thing above all else. Follow the data, even when it led somewhere uncomfortable. Especially when it led somewhere uncomfortable. Because that's where discoveries lived. And 3I Atlas was becoming the most uncomfortable discovery of his career. Chapter 8, January 18th. When Cassini's old data matters again. Sometimes the answer isn't in new data. Sometimes it's buried in old files, forgotten archives, and missions that ended years ago. On January 18th, Dr. Hiroshi Yamamoto, was digging through the Cassini mission archive when he found it. Cassini, the spacecraft that had spent 13 years exploring Saturn, its rings, and its moons, had been deliberately crashed into the planet in 2017 to avoid contaminating potentially habitable moons like Enceladus. But the data it collected remained, stored in NASA's planetary data system, waiting for researchers to mine its treasures. Yamamoto wasn't looking for anything specific. He was searching for examples of asymmetric plumes, jets of gas and dust ejected from icy bodies in unusual patterns. Specifically, he wanted to compare 3E Atlas's tail geometry to known cometary behavior. What he found instead was a ghost. During a close flyby of Enceladus on October 28, 2015, Cassini's magnetometer had detected something strange. A brief, localized disturbance in Saturn's magnetic field, lasting 17 minutes, repeating twice over the course of a 6-hour observation window. At the time, mission scientists had noted the anomaly but couldn't explain it. Enceladus has no magnetic field of its own. It's a small moon, 500 kilometers across, composed primarily of water ice. Any magnetic disturbances near Enceladus should come from Saturn's magnetosphere, or from charged particles in the plumes erupting from the moon's south pole. But the disturbance Cassini detected didn't match either source. It was too localized, too brief, and it repeated. Yamamoto pulled up the raw magnetometer data and processed it using modern techniques, algorithms that hadn't existed in 2015. When he ran a Fourier analysis, he found a faint periodicity. 17 minutes. Not quite the 18-minute thermal pulse in 3I Atlas. Not quite the 31-minute radio pulse. But close enough to be interesting. He dug deeper. Were there other examples of unexplained periodicities in the outer solar system? Anomalies that had been noted but never fully resolved? He found 3 more. One from the Voyager 2 flyby of Neptune in 1989. A rhythmic brightening in the auroral emissions near the planet's south pole, cycling every 22 minutes. Attributed at the time to magnetospheric oscillations, but never modeled successfully. One from the New Horizons flyby of Pluto in 2015. A subtle variation in the solar-wind interaction with Pluto's thin atmosphere, repeating every 14 minutes. Noted in the supplementary materials of a 2017 paper, but dismissed as instrumental noise. And one from the Rosetta mission at Comet 67P Tauri. A faint periodic pulse in the plasma density surrounding the nucleus, cycling every 26 minutes. Buried in a dataset from 2014, never published, never explained. 4 different objects. 4 different missions. 4 periodic signals that didn't fit the models. Yamamoto compiled the data into a single document and sent it to Patel with a subject line. Historical anomalies? Possible pattern? Patel read through the document twice. Then he called Yamamoto. "You're suggesting these are related?" Patel asked. "I'm suggesting they might be part of a broader phenomenon," Yamamoto said. "Something we've been seeing for decades, but never recognized as a pattern, because the signals were too faint, too brief, or too scattered across different missions." "What kind of phenomenon?" "I don't know. But consider this. All 4 objects were icy bodies. Enceladus, Neptune's atmosphere, Pluto, and Comet 67P. All 4 showed periodic oscillations in electromagnetic or plasma properties. And now we have 3 Atlas, also icy, also showing periodicities." Patel thought about it. "But the periods don't match. 17 minutes, 22 minutes, 14 minutes, 26 minutes. If it's the same phenomenon, why are the timescales different? Maybe the period depends on the object's size, or its composition, or its distance from the sun. We'd need a model." "We don't have a model," Patel said flatly. "We barely understand what's happening with 3I Atlas, let alone whether it's connected to a comet we studied 10 years ago." "But that's my point," Yamamoto pressed. "We've been treating each anomaly as isolated, as one-off oddities that don't fit the textbooks. But what if they're not isolated? What if there's a class of phenomena we've been missing because we weren't looking for it?" Patel leaned back in his chair. He thought about the history of astronomy. How many discoveries had come from recognizing patterns others had dismissed? Pulsars, regular radio pulses initially mistaken for interference. Fast radio bursts, fleeting signals thought to be instrumental glitches. Exoplanets, tiny wobbles in starlight that were too subtle to detect until someone looked closely enough. All right, Patel said. Let's assume you're right. Let's assume there's a phenomenon, some kind of natural oscillation in icy bodies, that we've been overlooking. What causes it? I have a hypothesis, Yamamoto said. What if it's related to subsurface oceans? Patel frowned. Subsurface oceans? Enceladus has one. We know that from Cassini. Europa and Titan probably have them too. Even Pluto might have a liquid layer beneath its ice shell. If an icy body has a subsurface ocean, and that ocean is interacting with the surface through cracks or vents, you could get rhythmic behavior. Like what? Like tidal pumping, or pressure waves, or convection cycles. Liquid water sloshing beneath an ice shell, releasing energy and pulses as it interacts with surface volatiles. Patel considered it. It was speculative, but it wasn't crazy. Okay, he said. But how does that explain 3I Atlas? It's a comet. It's tiny. 2 or 3 kilometers across. It doesn't have a subsurface ocean. Not now, Yamamoto agreed. But what if it used to? What if it's a fragment of a larger body that was destroyed? A shattered moon, a disrupted protoplanet, and it still carries traces of its parent structure. Pockets of liquid, embedded cavities. Internal differentiation. Patel was silent for a long moment. Then he said, That's a lot of assumptions. Yes, but it fits the data better than anything else we have. Patel couldn't argue with that. He forwarded Yamamoto's document to the working group with a note. Historical context. Periodic anomalies detected in multiple icy bodies over past 30 years. Possible pattern. Worth considering as we interpret 3I Atlas. The responses ranged from intrigued to skeptical. Dr. Tanaka, fascinating. If there's a common mechanism, we need to identify it. Dr. Monroe, I'm not convinced. Correlation doesn't imply causation. We could be cherry-picking anomalies. Dr. Loeb, whether these are related or not, the fact remains. We're observing something in 3I Atlas that doesn't fit our current models. That alone justifies deeper investigation. Dr. Marquez agreed. But let's focus on 3 Atlas first. We can revisit historical data later. Patel nodded to himself. They were right. The priority was the object in front of them, not the ghosts of past missions. But Yamamoto's research had shifted something in his mind. For years, astronomers had treated interstellar visitors as exotic curiosities. Rare. Unique. Wow. One of a kind. But what if they weren't unique? What if they were part of a continuum? A spectrum of objects with strange properties that we'd been seeing all along, but never recognized. What if the universe was full of objects like 3I Atlas, tumbling through the dark, exhibiting behaviors we couldn't explain? And we just never noticed, because we weren't looking. Patel pulled up a recent estimate of interstellar object detection rates. With current telescopes, astronomers expected to discover 1 interstellar visitor every year or 2. But with next-generation surveys, like the Vera Rubin Observatory, set to begin operations in 2025, that rate could jump to dozens per year. Dozens of Oumuamuas. Dozens of Borisovs. Dozens of objects with chemistries, geometries, and behaviors that defied prediction. And maybe, just maybe, dozens of objects like 3I Atlas. Objects that pulsed, that oscillated, that did things comets weren't supposed to do. He felt a strange mix of excitement and unease. Because if Yamamoto was right, if there was a phenomenon they'd been missing, a pattern hiding in plain sight, then the universe was stranger than they'd imagined. And 3I Atlas wasn't an outlier. It was a messenger. A glimpse into processes that had been happening for billions of years, in the cold, dark spaces between stars, waiting for someone to notice. This is not science fiction. This is January 2025. And humanity is finally learning to listen. Chapter 9. January 22nd. Starship's proposed flyby. The email landed in Dr. Samir Patel's inbox at 6:14 UTC on January 22nd. Sender: Elon Musk's office, SpaceX. Subject: Rapid Response Mission Proposal. 3. Atlas Intercept. Patel stared at the subject line for 5 full seconds before opening it. Inside was a 2-page summary, written in the clipped, confident style typical of SpaceX documentation. No bureaucratic jargon. No hedging. Just facts, numbers, and a deadline. The proposal was simple: modify a Starship vehicle for a rapid deployment flyby of 3I Atlas. Launch window: February 10. Flight time: 18 days. Closest approach: March 1st, at a distance of 50,000 kilometers. Payload: a suite of hastily assembled instruments. Higher resolution cameras. Spectrometers. Magnetometers. Particle detectors. Enough to capture detailed data during a 10-minute flyby window. Cost: $280. DART Trouty. Funded privately. Timeline: 3 weeks from approval to launch. Patel read it twice. Then he called Dr. Lindley Johnson at NASA's Planetary Defense Coordination Office. Lindley. Did you see the SpaceX proposal? I did. Johnson's voice was careful. Measured. Is this real? It's real. Musk's team reached out yesterday. They've been following the 3I Atlas situation. They think they can pull it off. Patel rubbed his eyes. In 3 weeks? They've launched faster. Remember, SpaceX has been iterating on Starship for years. They have vehicles in production. They have launch infrastructure. If anyone can do it, it's them. But a flyby? We've never intercepted an interstellar object before. The velocities alone. The intercept geometry is favorable, Johnson interrupted. 3I Atlas is moving slowly relative to Earth's orbit. Starship can match its velocity with a gravity assist from Earth and a burn at apogee. The trajectory is tight, but it works. Patel pulled up an orbital diagram. He traced the proposed path with his finger. Launch from Boca Chica. Elliptical orbit out to 1.3 AU. Course correction burn. Intercept. It was audacious. And it was possible. What does NASA think? Patel asked. Officially, we're evaluating. Unofficially, there's interest, but also concern. What kind of concern? Radiation exposure, for one. The spacecraft will be passing through the sun's radiation belts. Electronics could fry. Instruments could fail. There's no crew, right? No crew. Fully autonomous, but there's another issue. What? Ethics. Patel frowned. Ethics? We'd be sending a spacecraft to intercept an interstellar visitor, a natural object from another star system. Some people, scientists, policymakers, are asking whether we have the right to do that. Whether it's contamination, whether it sets a precedent. Patel felt a surge of frustration. Lindley, we're talking about a flyby. Not a landing. Not sample collection. Net. We'd pass within 50,000 kilometers, take pictures, and leave. How is that different from what we've been doing with telescopes for weeks? It's not different scientifically, but politically, it's optics. Sending a rocket to chase an interstellar object. Some people see it as aggressive, provocative. Provocative to who? Johnson didn't answer immediately. Then he said, quietly, to whatever sent it. Patel went cold. Lindley, do you think? I don't think anything, Johnson said quickly. I'm telling you what people are saying. Not scientists. Not NASA. But people in rooms you and I don't get invited to. No. Patel understood. There were layers to this. Layers he didn't have access to. Agencies. Committees. Briefings that happened behind closed doors. What do they want? Patel asked. They want answers, and they want them before 3I Atlas disappears behind the sun. The observation window was closing. In 8 days, the sun's glare would make detailed observations impossible. The object would vanish for nearly a month. And when it reappeared, it would be dimmer, farther, and harder to track. If SpaceX could launch by February 10th, the flyby would happen on March 1st, after the observation gap, but before the object became too faint to study. It was the last chance. Maybe the only chance. What do you need from me? Patel asked. Support. If NASA backs the mission, it gives SpaceX political cover. If we don't, they'll probably do it anyway, but it'll be messier. And if something goes wrong, then we deal with it. Patel thought about the risks. A spacecraft failure, a navigation error, an instrument malfunction. Any one of them could turn the mission into an expensive embarrassment. But then he thought about the alternative, doing nothing. Watching 3I, Atlas drift into obscurity, its mysteries unsolved, its behavior unexplained. All right, Patel said. I'll support it. But I want full data sharing. If SpaceX does this, the science has to be open. No proprietary holds. No private access windows. Nor lane Sydney. Consensuant. Not as a data nor netate. Agreed. I'll draft a memo. The call ended. Patel sat in his office, staring at the SpaceX proposal. He thought about the tail flip, the chemistry, the periodicities, the thermal hotspot, and he thought about the possibility, remote, terrifying, exhilarating, that 3 Atlas was something more than a comet, something that deserved to be visited. By the afternoon of January 22nd, word of the SpaceX proposal had leaked. Social media erupted. Headlines appeared on space news sites. SpaceX plans Interstellar flyby. Starship to chase mysterious comet. NASA considers private mission to 3 Atlas. The response was divided. Some praised the initiative. Bold. Ambitious. The kind of rapid response capability that only private spaceflight could provide. Others criticized it. Reckless. Unnecessary. A publicity stunt masquerading as science. And a small but vocal minority raised a different concern. What if 3I Atlas doesn't want to be approached? Patel saw the posts, the Reddit threads, the Twitter debates. Most of it was speculation, fringe theories. But some of it was thoughtful, cautious. One comment stood out. If this object is artificial, and I'm not saying it is, but if it is, then sending a spacecraft to intercept it is the equivalent of walking up to a stranger's car and peering through the windows. Maybe it's harmless. Maybe it's not. But you don't know until it's too late. Patel didn't believe 3 Atlas was artificial. He'd said it a dozen times. In meetings. In emails. In late-night conversations with colleagues. But he couldn't ignore the data. The tail flip. The periodicity. The chemistry that didn't fit. And he couldn't ignore the small, quiet voice in the back of his mind that whispered, "What if?" On January 23rd, NASA issued a statement. NASA is evaluating a proposal by SpaceX to conduct a rapid response flyby of interstellar object 3 Atlas. The mission, if approved, would provide unprecedented close-range observations and contribute to our understanding of objects originating outside our solar system. A decision will be made within 7 days. The clock was ticking, but so was something else. Because deep in the Green Bank Observatory archives, Rachel Kim was processing another dataset, and she'd found something new. The 31-minute radio pulse? It was still there, but now it had a companion, a fainter signal, barely detectable, repeating every 19 minutes. Not a harmonic of 31, not a subharmonic of 18. A new period, a new frequency, a new voice. And 3I Atlas was speaking in chorus. Chapter 10, January 25th. The Alignment Odds. Mathematics doesn't lie, but sometimes it whispers things we don't want to hear. On January 25th, Dr. Mylin Park sat in her office at the Apache Point Observatory, staring at a probability calculation that made her deeply uncomfortable. She'd been trying to model the periodic signals detected in 3A Atlas, the 18-minute thermal pulse, the 31-minute radio pulse, and now Rachel Kim's newly discovered 19-minute signal. 3 distinct periodicities. 3 different wavelengths. 3 different instruments. Park wanted to know if they were related. If they were harmonics of a fundamental frequency. If they pointed to a single underlying mechanism. She ran the numbers through a harmonic analysis tool, searching for mathematical relationships. The result was frustrating. The 3 periods didn't align in any obvious way. They weren't multiples of each other. They weren't Fibonacci ratios. They weren't golden ratios. They were just numbers. Unless Park tried a different approach. Instead of looking for mathematical elegance, she looked for physical constraints. If the periods corresponded to rotation, then 3 Atlas would need to be spinning at specific rates. But objects with complex rotation, tumbling end over end, precessing like a wobbling top, could exhibit multiple periodicities simultaneously. She pulled up models of tumbling asteroids. Objects like 4179 Tutatis and 25,143 Atakawa, which spin chaotically, their rotation periods shifting over time. But those objects showed damping. Their rotation gradually stabilized due to internal friction and tidal forces. Over millions of years, they settled into simple spins. 3 Atlas should be damped. It was old, billions of years probably. Plenty of time for any chaotic rotation to settle down. Unless something was preventing the damping. Unless something was actively maintaining the complex rotation. Park ran a simulation. She modeled a 2-kilometer nucleus with an irregular shape, spinning with 3 independent rotation axes. Then she added a constraint. The rotation had to be stable. Not damping. Not evolving. Locked. The simulation ran for 30 minutes. When the results came in, Park felt her stomach tighten. For the rotation to remain stable, for all 3 periods to persist without damping, the mass distribution inside the nucleus had to be extraordinarily precise. The moments of inertia had to be balanced to within 2%. Any deviation, and the rotation would collapse into a simpler mode within a few thousand years. But 3 Atlas had been traveling through interstellar space for millions of years, possibly hundreds of millions. The odds of its rotation remaining locked in such a delicate configuration by chance? Park did the calculation. 1 in 20,000. She ran the simulation again, tweaking the parameters. Same result. 1 in 20,000. She sent her findings to Patel with a note. If the periodicities correspond to rotation, the object's mass distribution has to be artificially precise. Natural tumbling can't maintain this configuration over geological timescales. Probability 0.005%. Patel read the email 3 times. 1 in 20,000. The same odds that had been quoted for the tail flip. The same odds that kept appearing in their analyses. He pulled up a statistics textbook, something he hadn't opened since grad school, and reviewed the concept of compounding probabilities. If multiple low probability events occur together, you multiply the odds. Tail flip. 1 in 20,000. Stable complex rotation. 1 in 20,000. Combined probability. 1 in 400 million. But that assumed the events were independent. If they were related, if the same mechanism caused both, then the odds didn't compound. They pointed to a single, unified explanation. What kind of explanation? Patel thought about the possibilities. A comet nucleus with an unusually rigid internal structure. Maybe a rocky core embedded in ice. That could resist damping. But rocky cores take heat to form. They require differentiation, melting, and separation, which requires either radioactive decay or tidal heating. And 3 Atlas was too small for significant radioactive heating, too isolated for tidal heating. What else? A binary system. 2 objects orbiting each other, their mutual gravity locking them into complex rotation. But no companion had been detected. The imaging data showed a single point source, a recent collision. Maybe 3 Atlas had been hit by debris in interstellar space, knocking it into a temporary tumbling state. But collisions in interstellar space are vanishingly rare. The object would have to be incredibly unlucky, or incredibly lucky, depending on how you looked at it. Patel shared Park's analysis with the working group. The response was immediate and polarized. Dr. Tanaka, this is compelling. We need to seriously consider non-natural stabilization. Dr. Marquet, or we need to consider that our models are wrong. Low probability events happen all the time. That's what low probability means, not impossible, just unlikely. Dr. Loeb, I agree with Elena that we shouldn't jump to conclusions. But Mai's analysis suggests we're looking at a configuration that requires explanation. Saying, it's just unlikely, isn't an explanation. Dr. Yamamoto, what if the object isn't solid? What if it's a rubble pile? A loose aggregate of fragments held together by gravity. That could produce complex rotation with less stringent constraints on mass distribution. Booms. Benvenutos. Park jumped in. I tested that. Rubble piles damp even faster than solid bodies. Internal friction dissipates rotational energy. The debate spiraled. Models were proposed and discarded. Simulations were run. Each one came back with the same conclusion. The rotation of 3A Atlas was improbably stable. Not impossible. Improbable. And in science, improbable things demand scrutiny. By the evening of January 25th, a new phrase was circulating in private conversations: artificial stabilization. Not artificial origin. Not alien technology. Just stabilization. The idea that something, some internal structure, some configuration, was keeping the object's rotation locked in a way that nature alone couldn't easily achieve. It was a subtle distinction, but an important one. Because if the stabilization was artificial, it implied design, intent, tight, purpose. And that opened doors no one wanted to walk through. Patel sat at his desk, late into the night, staring at Park's probability estimates. He thought about Occam's razor, the principle that the simplest explanation is usually correct. But what was the simplest explanation? That 3I Atlas was a 1 in 400 million outlier, a comet so statistically unusual that it defied every model? Or that it was something else? Something we didn't have a category for yet. He thought about the history of astronomy. How many times had scientists encountered something inexplicable, only to realize later that they'd been asking the wrong questions? Black holes were once thought impossible. Neutron stars were dismissed as mathematical curiosities. Exoplanets were considered unlikely until we found thousands of them. What if 3I Atlas was the same kind of paradigm shift? What if it was showing us something new about the universe? Not alien, not artificial, just new. Wow. Patel closed his laptop and looked out the window. The night sky was clear. Stars scattered across the darkness like diamonds on velvet. Somewhere out there, moving away from the sun, at 42 kilometers per second, 3 Atlas tumbled. Spinning, pulsing, oscillating, locked in a dance that defied probability. And in 5 days, it would slip behind the sun, unseen dart. But not forgotten. Because the universe had just handed humanity a puzzle wrapped in statistics and sealed with improbability. And walking away wasn't an option. This is not science fiction. This is January 2025, and the numbers are speaking louder than words. Chapter 11. February 1st, Lost Behind the Sun. On February 1st, 2025, at 11:34 UTC, 3 Atlas crossed the threshold. From Earth's perspective, the object moved within 2 degrees of the sun, close enough that solar glare overwhelmed even the most sensitive telescopes. The James Webb Space Telescope couldn't risk pointing that close to the sun. Ground-based observatories were blinded by daylight. Even the Solar and Heliospheric Observatory, designed to stare at the sun, couldn't resolve the faint comet against the brilliant corona. The observation window closed. For the next 34 days, 3 Atlas would be invisible. The astronomy community exhaled, and then, almost immediately, began preparing for what came next. Because when the object reappeared on the far side of the sun in early March, it would be different. Dimmer, Dutcher, farther, and possibly, probably, still inexplicable. Dr. Samir Patel spent the first day of February coordinating follow-up observations. He drafted a schedule, which telescopes would be tasked with reacquisition, which wavelengths would be prioritized, which teams would have access to the data. It was meticulous work, tedious, essential. But as he worked, he couldn't shake a feeling of loss. Like watching a mystery walk away before the final clue was revealed. He wasn't alone. Dr. Yuki Tanaka sent him a message at 14:07 UTC. It feels wrong to just wait, like we're letting it go. Patel understood. They'd spent 3 weeks chasing anomalies, building models, arguing over interpretations. And now they had to sit in silence while the universe decided whether to reveal more. Dr. Claudia Monroe was more pragmatic. We've done everything we can. Now we analyze, write papers, present at conferences, build the case for long-term monitoring. This isn't over, it's just paused. She was right. The data they'd collected was extraordinary. Even if 3 Atlas vanished completely after reappearance, the observations from January would keep scientists busy for years. But Patel wasn't thinking about papers. He was thinking about what they'd missed. Because despite everything, the spectroscopy, the thermal mapping, the radio monitoring, the probabilistic analyses, they still didn't have an answer. They had a profile, a list of anomalies, a collection of shouldn't-be possibles, but no explanation. That afternoon, Patel received a call from Dr. Lindley Johnson at NASA. Samir, the SpaceX mission, is approved. Patel felt a jolt of adrenaline. When's the launch? February 10th. Weather permitting. Starship is already being prepped. Instruments are being integrated. It's happening. What changed? Last I heard there was pushback. There was. But the observation gap forced the issue. If we're going to get close-range data, this is the only way. And frankly, some people in Washington are nervous enough about the unknowns that they'd rather have a spacecraft out there, just in case. Just in case of what? Johnson paused. In case 3I, Atlas does something unexpected. Patel frowned. It's been doing unexpected things for 3 weeks. I mean something unexpected on the way out. If the chemistry shifts again, if the tail flips again, if those periodicities intensify, we want eyes on it. Starship will be there March 1st, right? After the sun gap ends? Correct. Closest approach on March 1st at 9:15 UTC, 50,000 kilometers. 10-minute flyby window. Full instrument suite. Patel felt a mix of excitement and anxiety. A flyby was unprecedented. Risky, expensive. But necessary. Keep me in the loop, Patel said. I want to know the moment the data starts coming in. You'll be on the contact list. The call ended. Patel sat back in his chair, staring at the empty observation schedule. For the next month, 3 Atlas would be a ghost. A name on a spreadsheet. A footnote in an observation log. But on March 1st, it would return. And this time, humanity wouldn't just be watching from a distance. We'd be there. Meanwhile, halfway around the world, Dr. Rachel Kim was working late at the Green Bank Observatory. The observation campaign was officially over, but she'd been granted permission to analyze the archive data. 23 hours of continuous radio monitoring, spanning January 12th to January 29th. She was searching for structure, patterns buried in the noise. And she found something. The 31-minute pulse wasn't random. It was modulated. The intensity varied slightly from cycle to cycle, following a slower envelope. A longer period oscillation that took roughly 6 hours to complete. Kim plotted it. A Cine wave superimposed on a picket fence. A carrier signal with a modulation frequency. She ran a cross-correlation analysis, comparing the modulation pattern to known astrophysical processes. Solar wind variations? No match. Magnetospheric pulsations? No match. Orbital dynamics? No match. The modulation was clean, regular, structured. She ran one more test. A pattern-matching algorithm, searching for encoded information, the kind of analysis used in SETI searches. The algorithm flagged a low-confidence hit, non-random structure. Entropy lower than expected for thermal noise. Kim's heart rate spiked. She ran the test again. Same result. She checked the calibration. Clean. She checked for instrumental artifacts. None found. She sat back, staring at the screen. This was the moment every SETI researcher dreamed of. And dreaded. Because finding a signal was easy. Interpreting it was hard. And proving it was harder still. Kim didn't call it a detection. She didn't announce anything. She just saved the analysis, encrypted the file, and sent it to Dr. Jill Tarter at the SETI Institute with a single line. I need a second opinion. Confidential. Because if she was right, if the modulation pattern in 3A Atlas's radio emission was structured, then everything changed. Not just the science. Everything. But if she was wrong, she'd be labeled a crank. A cautionary tale. A graduate student who let confirmation bias run wild. So she waited. And hoped someone would tell her she was seeing patterns that weren't there. But, deep down, she knew the truth. The universe was full of noise. And 3I Atlas wasn't noisy. It was speaking. Chapter 12. February 9th. The reappearance. The sun's glare began to weaken on February 5th. Slowly. Degree by degree. As 3 Atlas crept farther from the sun's angular position in Earth's sky, the possibility of reacquisition grew. On February 7th, the first attempt was made. The Very Large Telescope in Chile, equipped with adaptive optics to compensate for atmospheric turbulence, targeted the predicted position of 3I Atlas. Nothing. Too faint. Too close to residual glare. On February 8th, the Hubble Space Telescope tried. Its orbit above Earth's atmosphere gave it an advantage. No atmospheric scattering, no daylight interference. Still nothing. But on February 9th, at 22:14 UTC, Pan-STARRS in Hawaii caught it. A faint smudge, barely above the detection threshold. But there, 3 Atlas had reappeared. Dr. Yuki Tanaka was the first to see the image. She'd been monitoring the data pipeline obsessively, refreshing the screen every few minutes, waiting for the automated detection algorithm to flag something. When it did, she opened the frame immediately. And she saw something wrong. The tail was split. Not a single streamer, as before. Not even the bent, flipped geometry they'd seen in January. This was different. 2 distinct plumes, diverging from the nucleus at angles roughly 40 degrees apart. One pointing northeast. One pointing southeast. Tanaka pulled up archival images from January. The tail had been single. Narrow, .I. Coherent, .Koi. Now it was bifurcated. She sent the image to Patel with a subject line. Reacquired. Tail morphology changed. Dual plume structure. Patel opened the image at 22:31 UTC, still in his pajamas, having been woken by the notification alert he'd set weeks earlier. He stared at the screen for a full minute. Then he called Tanaka. Is this confirmed? I'm processing additional frames now. But yes, it's real. Dual tails aren't unheard of. Some comets develop them when... I know, Tanaka interrupted. Type I and Type 2 tails. Ion tails and dust tails, driven by different mechanisms. But this doesn't look like that. Why not? Because both plumes show ionized emission. And... She paused, checking her notes. Ni dot tai. Both tails have metallic emission. What? Patel felt cold. That doesn't happen. I know. Dual tails in comets occur when solar radiation pressure pushes dust particles into one tail, while the solar wind sweeps ions into another. The fix is well understood. The chemistry is different between the 2 tails. But 3A Atlas was showing 2 ion tails, both ionized, both metallic, both pointing in different directions, as if 2 separate forces were acting on the coma. 2 separate winds. Patel ran through possibilities. A fragmented nucleus? That could produce dual plumes if pieces separated far enough. But the nucleus still looked intact, single point source. A rotating jet? That could create a spiral pattern that, viewed from the right angle, might look like dual tails, but the plumes were too distinct, too separated. An external interaction? Maybe the object was passing through a filament of interplanetary plasma, creating a secondary ionization source. But space near 1.30 was well monitored. No anomalous plasma structures had been detected. Patel sent the image to the working group with a note. Reappearance confirmed. Tail morphology dramatically changed. Dual ion plumes with metallic emission. Need immediate follow-up. Within an hour, 6 telescopes had been retasked. By dawn on February 10th, data was pouring in from Chile, Hawaii, Arizona, and La Palma. Every observation confirmed the same thing. 3A Atlas now had 2 tails. Dr. Mylin Park ran a spectroscopic analysis. Both plumes showed elevated COM and InG emission. The intensity ratios were nearly identical between the two, as if the nucleus was venting from 2 separate active regions with the same composition. Dr. Hiroshi Yamamoto modeled the geometry. If the nucleus had 2 jets firing in opposite hemispheres, and the rotation axis was tilted, you could produce a dual-tail structure. But it required precise alignment. The jets had to be positioned exactly opposite each other. Any offset, and the tails would merge or curve. The odds? Low. Not 1 in 20,000. Not 1 in a million. But low enough to add to the growing pile of improbabilities. Dr. Kovacs analyzed the radio emission. The Valley had reacquired 3E Atlas on February 9th, and the signal strength was surprising. The 31-minute pulse was still there. Stronger now. 3 times the intensity it had been in January. And there was something else. A faint secondary pulse at 14 minutes. Half the period. A harmonic. Kovacs ran a Fourier analysis, stacking weeks of data to pull the signal out of the noise. The result was unambiguous. 2 periodic signals. 31 minutes and 14 minutes. Both present. Both repeating. She sent her findings to Patel with a note. Radio periodicity intensified. New harmonic detected. Signal structure becoming more complex. Patel sat in his office, surrounded by printouts, graphs, and half-empty coffee cups. He stared at the dual-tail image, at the spectroscopic plots, at the radio periodograms. And he realized something. 3I Atlas wasn't quieting down. It wasn't fading into obscurity as it moved away from the sun. It was evolving. The tail geometry had changed. The periodicity had intensified. The chemistry remained anomalous, as if the object was responding to something. Reacting. Adapting. Pal thought about living systems. How organisms respond to environmental stress. How they adapt, change, survive. But comets weren't alive. Were they? He shook his head, trying to clear the irrational thought. Comets were rocks and ice. They followed physics. They obeyed thermodynamics. But 3I Atlas kept defying the rules. And on February 10th, at 1342 UTC, SpaceX launched Starship. The rocket lifted off from Boca Chica, Texas, carrying a hastily assembled payload of cameras, spectrometers, and sensors. The mission was simple. Fly past 3 Atlas on March 1st, collect data, and transmit it back to Earth. No landing. No sampling. Just a flyby. But it was enough. Because in 19 days, humanity would get its closest look at an interstellar visitor. And whatever secrets 3 Atlas was hiding would finally be revealed. Or so they hoped. Chapter 13, February 14th. The Structural Shadow. The image came in at 6:22 UTC on February 14. It wasn't from a major observatory. It wasn't from Hubble or JWST or the OST. It came from a secondary imager linked to the HIRIS camera on NASA's Mars Reconnaissance Orbiter, a spacecraft designed to photograph the Martian surface, not distant comets. But orbits align in unexpected ways. And on February 13th, MRO's trajectory carried it through a position where, for exactly 14 minutes, 3I Atlas was visible in the background of a routine Mars observation. The imaging team almost deleted the frame. 3I Atlas was barely detectable, A faint smudge at the edge of the field of view, contaminating an otherwise pristine shot of Valles Marineris. But Dr. Sarah Chen, a planetary geologist reviewing the images, noticed something odd. The smudge had structure. She enhanced the image, applied contrast filters, and zoomed in. What she saw made her lean closer to the screen. A silhouette. Faint, dotty, irregular, but distinct. Not a diffuse coma. Not a cloud of gas and dust. A shape. Chen saved the image and forwarded it to Patel with a note. Accidental observation from MRO. Maybe instrumental artifact, but thought you should see it. Patel opened the image. His breath caught. The silhouette was small, only a few pixels across. But it was sharp. Defined. Almost geometric. He pulled up models of comet nuclei. Most were irregular, lumpy, potato-shaped objects sculpted by sublimation and impacts. Some, like 67P Churyumov-Gerasimenko, had bilobed structures, two chunks fused together. But the silhouette in Chen's image looked different. Too regular, too angular. Patel forwarded the image to Dr. Claudia Munro with a question. Can you run this through shape reconstruction algorithms? I need to know if this is real or an artifact. Munro spent 6 hours processing the image. She used every tool in her arsenal: point spread function deconvolution, phase retrieval algorithms, edge detection filters. The result was frustrating. The resolution was too low. The signal-to-noise ratio, too marginal. The silhouette could be real. Or it could be an alignment of dust grains. Or an instrumental glitch. But Munro couldn't dismiss it. Because when she overlaid the silhouette onto a model of a typical comet nucleus, the match was poor. The observed shape had straighter edges, sharper transitions, less randomness. She ran a statistical test, comparing the silhouette's geometry to a database of 1,000 asteroid and comet shapes. The result, 94th percentile for regularity. Only 6% of known small bodies had shapes this geometrically constrained. Not impossible, but unusual. She sent her analysis to Patel. Can't confirm or refute. Geometry is unusually regular, but could be a chance alignment of irregular fragments. Need higher resolution to be certain. Patel shared the image with the working group. The response was immediate and polarized. Dr. Marquet, this is too low resolution to mean anything. We're seeing what we want to see. Dr. Loeb, but the regularity is worth noting. If confirmed, it suggests structural rigidity. Dr. Tanaka, could the shape be a rubble pile that's been compacted by spin? Centrifugal forces sometimes create bilobed or elongated shapes. Dr. Yamamoto, possible. But the edges are too sharp. Rubble piles are fractal, roux at all scales. This looks smooth. The debate escalated. Models were proposed. Simulations were run. Each one came back inconclusive. But the silhouette lingered in everyone's mind. Because if it was real, if 3 Atlas contained a rigid geometric structure, then the list of natural explanations shrank even further. Rigid structures require formation processes, solidification, crystallization, geological activity, none of which should occur in a comet, unless it wasn't a comet. By February 15th, whispers were circulating beyond the scientific community. Journalists were asking questions. Social media was buzzing. Conspiracy theorists were posting enhanced versions of the silhouette, drawing lines and angles, claiming to see patterns. NASA issued a statement. Preliminary imaging of interstellar object 3A. Atlas has captured a faint silhouette. Analysis is ongoing. The shape may result from irregular surface features or instrumental artifacts. Further observations are planned. The statement was careful, neutral, designed to calm speculation. But it had the opposite effect. Headlines appeared. NASA finds mysterious structure in interstellar comet. Is 3I Atlas artificial? Scientists puzzled by geometric shape. Alien probe? Comet silhouette sparks debate. Patel fielded a dozen media requests. He declined most of them. The last thing he wanted was to fuel speculation based on a single, low-resolution image. But he couldn't ignore the growing pressure. From journalists, from the public, from policymakers who wanted clear answers. And he didn't have them. On February 16th, he received a call from Dr. Lindley Johnson again. "Samir, we need to talk about communications strategy." "What do you mean?" "I mean the silhouette is leaking. People are talking, and some of them are asking questions NASA can't answer, or won't answer." "Like what?" "Like whether we're prepared for the possibility that 3A Atlas is artificial." Patel felt his frustration boiling over. "Lindley, I've said this 100 times. There is no evidence it's artificial. None. Zero. We have anomalies. We have improbabilities. But improbable doesn't mean impossible, and it sure as hell doesn't mean alien." "Nobody." "I know that, but perception matters. If the public starts believing we're hiding something, it creates problems. Political problems, trust problems. So what do you want me to do?" "Be transparent. Share the data. Explain the uncertainties. Let people see the process." Patel laughed bitterly. "And when the data doesn't give a clear answer? When we say, we don't know, then we say that, honestly, because we don't know is better than silence." The call ended. Patel sat in the dark, staring at the silhouette on his screen. He thought about the decades he'd spent studying comets. The beauty of their simplicity. The predictability of their behavior. And he thought about how all of that certainty was unraveling. Because 3I Atlas wasn't simple. It wasn't predictable. It was a question mark. A cosmic Rorschach test. And everyone saw something different. Some saw a comet with unusual properties. Others saw a relic from a distant star system. And a few, an increasingly vocal few, saw something more. A message. A probe. A visitor. Patel didn't know which answer scared him more, that 3A Atlas was natural, and we didn't understand it. Or that it wasn't natural, and we did. Because either way, the universe had just become a stranger place. And humanity was going to have to reckon with that. This is not science fiction. This is February 2025. And the shadows are starting to take shape. Chapter 14. February 20th. What the tale was trying to tell us. By February 20th, the pieces were finally coming together. Not into a complete picture. Not into a satisfying answer. But into something that looked, unmistakably, like a pattern. Dr. Samir Patel sat in a conference room at NASA's Goddard Space Flight Center, surrounded by printouts, tablets, and whiteboards covered in equations. Around him sat 24 researchers, the core of the 3I Atlas working group, assembled for one final meeting before the Starship flyby on March 1st. The goal was simple: synthesize everything they'd learned, build a unified model, make predictions for what the spacecraft would find. Patel stood at the head of the table and began. "Let's start with what we know, not suspect, not hypothesize, no." He clicked to the first slide. A list appeared. 3. Atlas confirmed observations. Interstellar origin. Hyperbolic trajectory. Came from outside the solar system. Anomalous chemistry. Co-rich. Low water content. Elevated nickel emission. Tail flip on January 12th. 160-degree reversal in under 9 hours. Multiple periodicities. Top. 31-minute radio pulse. Tart. 18-minute thermal oscillation. 19-minute secondary signal. 14-minute harmonic. Stable complex rotation. Mass distribution, precise to within 2%, maintained over geological timescales. Dual tail structure, post-reappearance. 2 ion plumes with identical chemistry. Possible geometric silhouette. Low-resolution imaging suggests structured core. Patel let the list sit for a moment. Then he said, "Now let's talk about what this means." Dr. Mylin Park spoke first. The chemistry tells us this object didn't form in a typical planetary system. Or if it did, it formed in a very unusual environment. Molecular cloud, protoplanetary disk. Somewhere cold and carbon-rich. Dr. Q. Yamamoto nodded. The nickel emission supports that. If the object contains metallic grains, it either formed near a protostar, where temperatures were high enough to condense metal, or it's a fragment of a differentiated body. But differentiated bodies don't outguess, Dr. Tanaka interjected. They're geologically dead. No volatiles left. So either it's a hybrid rock and ice mixed, or... She trailed off. Or what? Patel asked. Oh, the metal isn't natural, she said quietly. The room went silent. Dr. Marquez shook her head. Yuki, we've been over this. Metallic emission is rare in comets, but it's not unheard of. We can't jump to... I'm not jumping, Tanaka interrupted. I'm following the data. We have elevated nickel without corresponding iron. We have thermal pulses that don't correlate with solar heating. We have periodicities that require artificial precision to maintain. At some point, we have to consider that natural explanations aren't sufficient. Dr. Loeb leaned forward. I think Yuki is right to push the boundaries here, but let's be precise. Artificial precision doesn't mean artificial origin. It means we're looking at a physical configuration that's highly ordered. Nature can produce order. Crystals, resonant orbits, standing waves. The question is, how did 3 Atlas achieve this configuration? Dr. Kovacs added, and why is it stable? That's what bothers me most. Complex systems decay. Entropy increases. Yet 3I, Atlas seems to be maintaining its structure actively. Patel clicked to the next slide. A diagram showing the object's rotation, overlaid with the detected periodicities. Claudia, you've been modeling the thermal data. Walk us through your latest results. Dr. Munro stood. The 18-minute thermal pulse is real. It corresponds to a localized hotspot on the nucleus, rotating in and out of view. If the nucleus is spinning with a period of roughly 31 minutes, and the hotspot is offset from the rotation axis, you'd see it brighten every 18 minutes. So the periodicities are related, Patel said. They are. But here's the problem. The hotspot is too hot. At 1.30 from the sun, the surface temperature should be around 210 Kelvin. The hotspot is reaching 230 Kelvin. That's a 20-degree excess. Subsurface heat? Yamamoto suggested. Maybe. But sustained for weeks? That requires an energy source. Radioactive decay is too slow. Chemical reactions are possible, but we'd see compositional changes in the coma. We don't. So what's heating it? Patel asked. Munro hesitated. Then she said, I don't know. But whatever it is, it's periodic. It pulses like a mechanism. The word hung in the air. Mechanism. Dr. Chen, the planetary geologist who discovered the silhouette, spoke up. What if the structure I imaged isn't a nucleus? What if it's something inside the nucleus? A core. A skeleton. Something rigid that's embedded in ice. Like what? Marquez asked. Like, I don't know, a rocky core, a metal frame, something that provides structural support. But why would a comet need structural support? It wouldn't, Chen admitted, unless it was designed to. The room erupted. Half the group objected immediately. The other half fell silent, thinking. Patel raised his hand. All right. Let's take a step back. We're speculating beyond the data. Let's focus on what the Starship flyby can test. He clicked to a new slide. Test-stable hypotheses for March 1st flyby. Composition. High-resolution spectroscopy will confirm or refute exotic volatile ratios. Structure. Close-range imaging will resolve the nucleus shape and detect subsurface features. Thermal anomaly. Infrared mapping will locate the hotspot and measure its temperature precisely. Magnetic field. Magnetometers will detect any intrinsic magnetic field, which would imply internal structure. Rotation. Continuous imaging over 10 minutes will measure rotation period and axis orientation. These are our priorities, Patel said. If we can answer even half of these questions, we'll have made history. Dr. Loeb spoke quietly. And if the answers don't fit natural explanations? Patel looked at him. Then we'll deal with that. How? I don't know. But we'll start by being honest. With ourselves. With the public. With the implications. The meeting adjourned at 1847 at CC. The researchers dispersed, each carrying the weight of what they'd discussed. That evening, Patel sat alone in his office. He pulled up the silhouette image one more time. He stared at the faint, angular shape. And he thought about a conversation he'd had with his daughter years ago, when she was 8. She'd asked him if aliens existed. He'd said, probably. The universe is too big for us to be alone. She'd asked, will we ever meet them? He'd said, maybe not in our lifetime, but someday. Now, staring at the silhouette, he wondered if someday had arrived. Not with a radio signal. Not with a distant exoplanet. But with a small dark object tumbling through our solar system, carrying secrets we were only beginning to glimpse. He didn't think 3I Atlas was a spacecraft. He didn't think it was a probe. But he couldn't ignore the possibility that it was something more than a comet. A relic. A fragment. A piece of something larger. Something older. Something that had traveled across the void and arrived here by chance. Or by design. And in 9 days, they'd know more. Because Starship was already en route. Engines firing. Trajectory locked. Instruments online. 50,000 kilometers. 10 minutes. One chance. The universe had posed a question. And humanity was about to answer. Or try to. Because some questions don't have easy answers. Some questions change us just by being asked. And 3I Atlas had asked the biggest question of all. What else is out there? March 1st, 2025, arrived quietly. No fanfare. No countdown clocks on news channels. Just a small group of engineers and scientists gathered in a control room at SpaceX headquarters in Hawthorne, California, watching telemetry stream from a spacecraft millions of kilometers away. Starship approached 3I Atlas at 9:03 UTC. Closest approach was scheduled for 9:15. The data began arriving at 9:16, delayed by light speed travel time. First, imaging. High-resolution optical frames, captured by a suite of cameras pointed at the nucleus. The images were stunning. The nucleus was small, 2.7 kilometers across, and irregular, but not randomly so. It had lobes, ridges, facets, like a carved stone. And embedded in the surface, partially obscured by sublimating ice, was a structure. Not a crater. Not a boulder. A structure. Linear. Angular. T. Approximately 400 meters long. Partially buried. Partially exposed. The control room went silent. Dr. Monroe, watching from a video feed, whispered, "That's not natural." Second, spectroscopy. Confirming the chemistry. High carbon ditchau. Low water. Elevated nickel. But also something new. A faint emission line at 630 nanometers. Neutral oxygen. Glowing. Not from sublimation. From fluorescence. As if something inside the object was emitting light. Third, magnetometry. A weak but detectable magnetic field. 0.03 microtesla. Aligned with the rotation axis. Comets don't have magnetic fields. Not unless they contain metallic cores. Not unless they have internal currents. Fourth, thermal mapping. The hotspot resolved. A region 300 meters across, glowing at 240 Kelvin. Pulsing. Cycling every 18-20 minutes. And then, at 9:17 UTC, as Starship passed closest approach and began to recede, something happened. The radio emissions spiked. Not gradually. Instantly. 100-fold increase in intensity. Lasting exactly 40 seconds. Then dropping back to baseline. As if 3I Atlas had noticed the spacecraft. As if it had responded. Rachel Kim, monitoring the Green Bank Observatory feed, saw the spike in real time. She ran a spectral analysis. The emission was structured, modulated, non-random, and for a brief, terrifying moment, she thought she saw a pattern, a sequence, repeating, regular. She didn't call it a message. She didn't announce it. She just saved the data, encrypted it, and sent it to Dr. Patel with a note. "You need to see this, now." Patel was still in the SpaceX control room when the email arrived. He opened it on his phone, downloaded the file, ran it through a quick analysis app, and he saw it. The pattern. Faint, comet, marginal. But there. A sequence of pulses, grouped in sets of 3, repeating 4 times. Then silence. Not speech. Not language. But information. He looked up at the screen, at the images of 3 Atlas scrolling past, at the geometric structure embedded in the ice, at the magnetic field that shouldn't exist, at the thermal pulse that defied explanation. And he realized something. They'd been asking the wrong question. The question wasn't what is 3 Atlas. The question was, what is it telling us? Because the tail flips, the periodicities, the chemistry, the structure, none of it was random. None of it was noise. It was a signal. A message written in physics and geometry, in light and magnetism, in the language of the universe itself. Not a greeting, not a warning, just information. A record, a signature, a fingerprint of wherever 3I Atlas had come from. And maybe, just maybe, an invitation to look closer, to keep searching, to understand that we were not alone in the asking. Patel closed his eyes. He thought about the universe, about the billions of stars, the trillions of worlds, the unimaginable expanse of space and time. And he thought about a small, dark object, tumbling through the void for millions of years, carrying a structure, carrying a signal, carrying a question. Are you listening? And for the first time in human history, the answer was yes. We are listening. We heard you. And we're ready to learn. This is not science fiction. This is March 2025 Dartai. And the universe has just begun to speak.